Try now. Okay. So as I explained yesterday to one of your classmates, I had a very bad stomach problem, so I had to get a serum. So I was 6 hours yesterday receiving that in my vein. So still shaky a little bit. So the session that was originally planned for today for the evaluation couldn't be. So we're going to go with the material, and after this, you will be able to complete the last question of the assignment. Okay. Also, this morning we were working with Andy Miranda, trying to make it work, the shaker, but we couldn't for the random process. So hopefully by next week we will be able to do it. So I'll let you know about that. Okay. So let's go on. So the plan is today's session with this material, you will be able to complete a full assignment. Next Tuesday, we will have evaluation. And from that point, we will go on with especially the project, which is the big thing right now. Okay. If possible, at the end of this session, we will be able to talk about that a little bit. Okay. So I'm going to share like it. Excel, and I have opened. Can you see my PowerPoint presentation screen?
Yes, doctor.
Okay, so we were talking last session about the spectral density function, okay? I was trying to find in the literature a figure to try to explain what that is, and I couldn't. So I'm just going to make a quick sketch of that, okay? Remember that this is just a quick sketch, but I hope you will perceive the general idea. Okay. Stop this. I'm going to show you this. Okay. So this is the thing. Okay. In general, we think that we have several waves with different amplitudes and different frequencies. If we combine these, we have what we see in the open sea. Something. Okay. So we try to summarize this information with a spectrum. Okay. And for that, what we do is we analyze the energy distribution, basically. Okay. And we do that versus the frequency. So here we have that this is a wave, okay? And the wave basically has some energy. So the energy per unit area. Remember that the wave we have defined it as a 2D problem. So we see a wave, and in this direction, there is no change, right? So as you move upward, you are carrying some energy. Now, the problem is that since in that direction, there is no limit, right? The value of the energy is going to be infinite. So what we have to do is calculate that energy in a per area function. And that's what we're going to do, okay? So we're going to calculate the energy per unit area. Okay? Now, energy, it's F times L in general, right? And area is length squared. But we also have the density of the water, which is usually the value that we want, or I'm sorry, not the energy. I'm sorry, the specific weight of the water, right? Now, a specific weight is a number that doesn't change much, right? So I'm going to write it like this, okay? So in this way, we're going to work. So it's going to be the energy of the wave system per unit area, because as I said before, this is in this direction, there is no limit. So this value will be infinite. So if we divide it by the area, then square, we got something specific. And also, the specific weight of the water is about 1. So it doesn't change much. So we just divide it by that. Now, we're going to have L divided by L squared. And here we have L cubed. So the result is going to be 2, 4 is going to be L squared. Okay, so in general, we say this is energy, but it's not really energy. It's energy in a certain area of the sea, thinking that you have one single harmonic wave. And we divide that by the specific weight. So we get some simple thing. So in general, the spectrum is a distribution of the contribution of each one of these in terms of energy. But it's not really energy. It's energy per unit area and per unit specific weight. Okay? Here we're going to say that this is a spectrum. Remember, this is units of length squared. Okay? So we said this is for F1, this is for F2, and this is for Fn. So what we do here is we plot here this, and since we have, you can do this in hydrodynamics, I think we're going to do it later. This energy is going to be proportional to the square of the amplitude, right? So this one here, F2, is larger, so we're going to have something like this. And let's suppose that just starts declining like that. So this is for F1, this is for F2, and this is for Fn. More or less, that's what we call a spectrum. Now, immediately, you see that this distance here is very important. This is like delta F. Okay, so as usual, you choose a different delta F and you have a different result. What can we do? Instead of that, what we do is we calculate the energy divided by frequency, the frequency in increment. Okay, so what we are doing is we calculate this delta energy in this range we plot it like that, but since we depend on delta F, what we do eventually is divide this by delta F. And this energy is what we call spectrum. And in the title that I just presented, we work about spectral density. Okay, so spectral density, we call it with an S. So that's going to be a delta E. So that's the energy which we have in this increment, in this interval of frequency, and divided by the increment in frequency. Okay? Quite often, quite often, this F, we do not express like that, but we press it with a 2 pi. Okay, so this is frequency in radians per second. This is frequency in cycles per second. Okay, so this is the way we do it. So if delta E had units of length squared divided by 1 over time, so eventually the spectral density is this one here divided by the increment at which you included the energy in a certain interval. Are we clear, people? We clear? So when we convert that, I'm going to write this in another page. Okay. We have here, this is delta E, because we have this, we have that, this, and that. This is E. And then we convert that into a spectral density. We have to remember that delta E is equal to the spectral density times delta omega. So in this case, what we have is a continuous function there. And we know that this area corresponds to each one of these values. Okay, so this has units of length squared times time, and these are units only of length squared. Okay, so in general, people, in this class, we're going to say that we said a spectra, but in general, what we mean is spectral density. Okay, and if you include the units, there shouldn't be any confusion, right? Because I'm talking about the elevation of the surface, right? But in general, eventually you will see in the next chapter that we can calculate the spectral density of any parameter. Example, if you want to face a ship in a irregular sea, right? And you want to design the ship so that it doesn't break, it doesn't fail, the structure doesn't fail. What we have to do is we have to calculate the bending moment. But the bending moment is a result of a regular sea. Yeah, so we're going to calculate the bending moment, the spectral density of the bending moment. So in that case, this is not going to be L squared T. It's going to be FL squared times the time. Okay, but so far we are speaking about the elevation of the sea surface. So those are the units. Okay, so this is what we need to evaluate right now. Okay, so this is something that I needed to mention here. Let's go back now to our presentation. Can you see my PowerPoint slide?
It's not on full screen.
Not yet?
Not full screen.
It's what?
It's not on full screen.
Oh, it's not full screen. Okay, let me see if I can do it. It's not in full screen? People?
Not yet, doctor.
How about now? How about now?
No, no yet.
It is?
No,
not yet.
No. Oh man, I have to stop this thing. See this? This is my PowerPoint, right? This is my full. Now, people, can you see my full screen? Okay.
Yes, sir.
Thank you. There was somebody in the waiting room, Miss Freire. Would you please let him in? Okay, so that's the spectral density function, right? So every time you see a spectral density function, immediately you start thinking that, okay, I have a distribution of the energy as a function of frequency. And when we see a large value, that means that there is a lot of energy in this region of harmonic waves. And those are identified with the frequency, which is on the scale, on the X scale, okay? You have to remember also that this is more or less proportional to the square of the amplitude. We're gonna take advantage of that. So let's review what we saw, what we studied last week, okay? So this is what I was trying to explain to you. This is the definition, that's the formal definition, okay? This is the Fourier transform of the, in this case, we're talking specifically about the elevation of the Z surface. So this is a Fourier transform of that. And this is the complex conjugate. If you multiply one complex times its conjugate, the result is going to be the amplitude squared. So this is the amplitude squared of the Fourier transform of the wave elevation. That's what it is. Okay, and then we have to divide it by t. We usually take this very long. So this is very high, but this is also very, very large. So at the end, the two quotients of two very large quantities will give you one finite result, which is what we want. Okay? Of course, sometimes we cannot get too long a record, right? We have to accept something that we have. Some years ago, maybe 10 or 12 years ago, I directed a thesis. We made some measurements in a ship, in a Navy ship. It was a Navy officer who was taking the measurements. And then we proceeded those signals and all of that. And we tried to publish, okay, in one of the conferences in naming. And I always remember the first comment that they made us is that the records were too short. That just killed us because our records were too short. Anyway, so just to have in mind. Okay, now, let's go on. And since this is a function of the frequency, okay, we can try to see what do we obtain taking the inverse Fourier transform of this spectral density function. Okay, so when we calculate the Fourier transform, 1 over 2 pi, and the E has the exponent negative, e to the minus I omega t. In this case, it's positive because it's the inverse transform. Okay, let's see what we have. So we take this and put it into here and proceed the process. That's what we have. Okay, now this one here is the Fourier transform, but at the end, this is conjugate. So the Fourier transform, you integrate the function, which in this case is real, times e to the minus e to the I omega t. So the conjugate is just e to the plus I omega t. That's all. This is what we have here. So this is the definition that we presented at the beginning of this chapter. Now, we have an integration in time, we have an integration in frequency. What we do is we change the order of integrations, okay? So here we should integrate first in time, and the result is replaced here, and then we integrate in frequency. We can switch. And for that, you can recall from your math classes that the function has to be continuous and differential. And we assume that they are, okay? So we are going to integrate first in frequency, and then the result is going to be integrated in time. That's why in here, I employed a tau, not a time. Now, this thing here is the inverse of the Fourier transform because we see that this is positive. But instead of time, we have t plus tau. That's the result. And that's what we put in here. So at the end, this integration will give us this, that's that. And we recall that this is trying to relate the value of the function of the elevation at a certain time with the value of the same function, but at the interval ahead of t. And then we go on and on, on and on. We move, so the distance, the space between which I am trying to see the relation is constant, it's called tau. And that's what we call the autocorrelation function. We defined that last week. That's what we call R sub tau. So what we have shown is that the inverse Fourier transform of the spectral density is equal to the autocorrelation function. If we can go the other way, that means that the Fourier transform of the autocorrelation corresponds to the spectral density. Okay, we go in one and the other direction. It's unique, the relationship. And that's what we call the Wiener-Kirchheim relations. Please keep this in your memory. The Fourier transform of the autocorrelation is equal to the spectral density. The inverse of the Fourier transform of the spectral density corresponds to the autocorrelation function. Okay? Now, if we set tau equal to 0 in the autocorrelation function here, okay? Okay, if we set this tau equal to 0, this is going to be 0, and we're going to have zeta squared. That's the mean square. So that's why we take advantage of that. Okay, R tau equal to 0 here. R at tau equal to 0. Okay, for tau equal to 0, this is the inverse Fourier transform. That we see that because we have the positive sign here. And since this is the resulting variable, we want to take that value equal to 0. So we put 0 here. But this is equal to 1. That means that this is the result. And this is equal to the area behind the spectral density. Okay, so the area below the spectral density corresponds to the autocorrelation function at tau equal to 0. And if we make tau equal to 0, we have the mean squared. So that's what we call RMS squared. And if the mean of the function is 0, that's equal to the variance squared. Only when the variance is equal to 0, because we check that, right? That I said that that's a very common process. So you got the expected value of the function minus the mu squared is equal to E x squared minus mu squared. This is the RMS squared. And this is equal, I'm sorry, this is the mean squared. And this is 0, then these two are 0. And this is sigma squared. Okay? Please put that in your memory. This is usually the case in our calculations, right? Because, for example, you go to the left with the same frequency as you go to the right. You go up, same frequency as down. There are certain special cases. For example, when we were working some measurements in Galapagos, see, we measured the acceleration of inter-island fast boats. We have something like this. Very fast boats, right? So when you go up, that's because of the waves. When you come down, that's because of the gravity. So in general, the force because of the waves is much higher than the force because of the gravity. So in general, this did not allow us to have an average equal to 0. So it was very interesting. So when we plotted the acceleration, we have minus g here, and we have very high. So we have something like this. So our average was not 0. And the minimum value was very close to minus 9.8, minus 1g. Okay, so in this case. But that's a special case. Usually, this is the case that we are going to work. Okay, so the area under the spectral density function corresponds to the square. And in cases where the mean is 0, corresponds to the variance, or deviation raised to the second power. Okay, so please keep that in your memory. Okay, this is a figure. I took it from Professor Trosch's class notes. I think it's very, very, very useful. Okay, here we have the 3 functions that we have been mentioning during this presentation. Okay, here, let's suppose we have versus time, we have the result from a buoy. So the buoy goes up and down, and that's what we see here. Okay, and this is minus t over 2. This is large T. This is plus t over 2. Remember, t has to be very long. Otherwise, statistically, this is not useful. Okay, and we can see that we have some of these crests, right, which is very easy to recognize. So we can expect that this distance has to do something with a certain period that we call t sub 0. That's very important, because that tells us that since we have a crest, and another crest, and another crest, and they are more or less separated by a distance in time t0, that means that that can be related to a certain harmonic with that period. And when we analyze this is the autocorrelation, that has to be shown here. Because this value, which is very high, is related to this value, okay, at time t0. That's a very important, I mean, the product contributes a large amount in the integration. Now, if we go from this crest to the next one here, similar, because it's one crest, we jump the other, we check to the other. And so the distance 2t0 is going to also contribute a lot to the summation of this autocorrelation. And we see that this is classical shape. We have a first hump at d0, and then at the distance, at the same distance, 2t0, we also have a hump. At 3,0, similar. Okay? And then this goes to 0. That means that if we can check this with a very high value up here, this is not going to be related. It's very difficult to see any relationship between. And how do we go from here to here? So that's the definition of the autocorrelation function. We have to integrate from minus to plus, and we integrate t with t plus tau. The problem with this is that you have to change tau in a continuous way. That's very difficult to do. So what we can do is we can try to develop some numerical schemes in order to produce this function. And then this summation probably will produce very large values. Okay, so we divide it by 1 over the large or the total length of the integration limits. Okay, now with this, we just deduced the Wiener-King-Challenge relations. So we can take the Fourier transform of this, and we can calculate the spectral density. Okay, so this is the Fourier transform. So we put this function into here, and this is what we have to apply. This is the result. Or we can apply from here the definition of the spectral density, and we should get the same result. One thing is to desire to have the same result, and another very different thing is to have the same result. But anyway, let's prove that we obtain the same result. Okay, so for me, this is very useful because it summarizes the process that we have been reviewing. Is there any questions about these, people? Is there any question that I can answer? Is there any questions? Any questions, people? No? So I'm going to continue. There's something which is very, very, very important. We see that if z, okay, z of time is a real function, then result of this is symmetric. Okay, and that's what we see. I tried to mention that at the beginning of this chapter. That's not exactly correct. What we mean is the amplitude of the Fourier transform is symmetric. But in this case, we're taking the amplitude. So the result is going to be something like this. So instead of taking both sides, and this limit goes to infinity, okay, what we are going to do is just simply consider one side. And since we know that the area below here has some physical interpretation, okay, what we are going to do is take this area and put it in here. So this is what we mean by that. When we consider only one side, we call it S plus. Please, people, don't forget the plus. I'm going to be very strict on that. You have to write the plus if we consider only one side of the scale, of the axis. So for positive frequencies. And what we do is we take these values and put it into here. So at the end, the area here is equal to that, and we consider that using the 2. Okay? So from now on, this is very different. This is very different than that, because this only is valid for frequencies which are positive on the right-hand side of the axis. And that's quite useful because we have to integrate it to infinity. In this case, we have to go from minus infinity to plus infinity. That's a very long process. Okay, so we take advantage of that and we only work with the right-hand side. So we have only one infinity to go to instead of 2. That's a larger advantage. Okay, now units. So this is very important. People, what are units of the spectral density of zeta? See, we have zeta. In this case, we're talking about the elevation of the wave, the sea surface. Now we have zeta formed. What are units of this? Please turn on your cameras. I want to see your faces. I want to see that everybody's here, or I'm going to take them. Those who I cannot see just have to leave this session. That's it. Okay, Miss. Go on. Who was speaking? Length?
Length times second.
Length to the square. Okay. Is
yeah.
that correct? Is it?
Length to the square. Times second.
Times time.
Yeah, times time. But
Is it correct? No, I don't think so. Let me go back. Let me go back to the definition of the Fourier transform. Here it is. So what's the definition of Fourier transform? So we have, this is time. So this is the function. What are the units of the C-surface? What's the result of, what are the units resulting from this operation?
You have the length over time. Oh,
What are units of this? What are units of this?
oh, time.
Yeah, and what are units of this? In this case,
It's a time same.
that's length, because it's a wave elevation.
Oh yeah.
It's just, this is non-dimensional. This is non-dimensional, so it's just time times length. That's all what it is. But we have those are the units of okay, so we were here. So this is time squared, length squared. I'm sorry, this L time. So it's just one L and one time. That's all. What are the units of the spectral density? Mr. Iñiguez, what are the units of this spectral density? Mr. Iñiguez, please, your microphone is off.
Hello.
Okay, go on. Units of the spectral density function.
Over length over time.
Now, here I have length times time. This is also length times time. So this is length squared times squared divided by time. I'll give you length squared times time. If I integrate, what units do you obtain here, Mr. Manrique? What units do you obtain with this operation?
Length squared.
Yes, length squared. And that's correct because this corresponds to R0. And this is the autocorrelation. So it's RMS squared. Makes sense, right? Because we're talking about the elevation. So makes sense. Okay? So please keep these things in your memory, okay? Because this is, and units are extremely important. Now, we're talking about that we start with the record of the elevation of the sea surface. The problem is that we think, okay, if we want to calculate the response of the ship, we have to start by having this record of wave elevation. That's too much, right? So what can we do? What people have done is they have taken a lot of these records. They have calculated the spectral density and they have plotted. And then they have developed some curves, some regression curves that approaches these values were determined from experiment, or not from experiment, from a real world. And that's the formulation that I'm going to present here. I'm going to present only two formulations. which are the simplest one. Okay. Eventually, you can see in the literature there are some others. The first one I presented because extremely simple. For the academic purposes, it's very useful. I'll give you just one parameter, and with that parameter, you are able to develop the spectral density. That's very simple, right? And the other one uses two parameters. See, I attended a seminar some 5 or 6 years ago, and the instructor mentioned that in the US, United States, calculations in this area were developed using the other formulation. So it's a good idea that you have both. But you have to be aware that there are some others. Okay, so the first one is this name, Pearson-Moskowitz. It's very old. So he uses only one parameter. So here, you see that this is a constant. This is omega to the 5th power. This is omega. So this is radians per second. So this is the variable, the independent variable. This is g squared. So g has units of 981 meters per second squared. This is negative. Please be careful, okay? Because when we work with Excel, right, and you say minus x, and then you raise to the second power, the result he takes as positive because he's taking something like that. So we have to be careful. So when you implement this in Excel, you have to say minus x squared. And the result is going to be negative. Okay? Because this value can change very rapidly, and you can have tremendously large values because of that. Okay? I'm warning you to save you some time. Here, again, have G. We know that constant. V, that's the wind velocity. Meters per second. Okay, that's not the wind that I feel here in my hand. No, you have to measure 30 feet above the free surface. Okay? That's the velocity that you want. Okay, and again, you have omega, which is the independent variable. So if I give you a wind velocity in knots, you convert that into meters per second, and you can develop this operation. You can plot this graph with one single parameter. That's why it's so useful. Units. Everybody, get a paper and give me the units of this. International System of Units. Everybody. International System of Units. I want you to tell me what are the units of the spectral density, please. I'll give you 1 minute. Mr. Barbara, did you get it? Mr. Barbara, did you get it?
Yes, Doc.
What are the units?
The unit is L squared for
Times.
time. L squared.
Okay,
Meters.
so this is specifically for International System of Units. Okay, we have to be very careful because there are many publications and each one has different units. Especially if you take any reference from the US, they usually use different system of units, and that will change this and that constant. Okay, if you do that, see, we could have easily. So here we have omega, we have S plot, we have something like this. To the right, it's never zero. Of course, if this is very small, this is negative, this is going to be, I'm sorry, this is very close to zero. So you go in that direction and basically you go to zero. But it's never zero. It's just asymptotic. Okay? Now, here, you have this value, what we call the modal frequency. That's the frequency at which the spectral density has its maximum value. Okay? That's the modal frequency. And you will see that in the tables that I'm asking for your homework. Okay? In this case, what we can do is we can differentiate and we can demonstrate that this is equal to this value, 0.877 G over V. Okay, so that's the modal frequency specifically for the Pearson-Moskowitz formulation. Another formulation, that's from Schneider or ITTC with two parameters. Okay, so in this case, you have this formulation, and you can see that it is very similar to this formulation. Omega to the fifth, omega to the fifth. B to the fourth, B to the fourth. Negative, negative, exponential, exponential. Right? But in this case, we have two constants, A and B. And they depend on the parameters of the C state that we're talking about. So we have H sub S. Okay, this is the average of 1/3. How did we call the average of the largest 1/3? Anybody? Average of the largest 1/3?
The significant value.
The significant value. So this is, people, this is something that we mentioned earlier. H is height. Okay, because it's easier for somebody who is observing the waves to look at the crest, to look at the throw, and get the difference. If you want to calculate the amplitude, which is what we usually use, you have to imagine the zero line and then get the distance to the crest. So it's much easier. You see that, the crest, see the throw, and try to determine how much is this height. So this is a significant height. Okay? This is the mean period. We're going to define that probably not today, in next week. Raised to the 4th power. And here, the other constant B is also dependent on this T to the power. Okay? So these parameters that depend on the C state. Okay, so that's why I want you to find this table with the characteristic of the C state. So if I, in the project, for example, Engineer Dominguez will tell you, for example, it's important that you analyze the response, for example, in C state 4. Okay, so you have to look for, in the table, for C state 4, and you have to determine the average period and also the significant wave height. With these two values, you put it here and here, and you get something similar to this. Okay, and from that point, we can go on and make calculations. Okay, so in this way, it's much easier than instead of putting a wave buoy and measuring for a long time and then making these calculations, which are okay. Now here, instead of T average, I'm using omega Z. I have to, the omega Z is by definition 2 pi over T average. Okay, and this is what we call the frequency of zero crossing. So this is we'll define that in the next slide. So you can ask yourself, wait a second, we're talking about an average, a random process. How can you talk about average? Well, there's some ways to approximate. There are some ways to approximate. We will see that, how can we do it, okay? But eventually, what you can do is you can simply take these parameters from this table after you have specified the C state that you want to consider. Okay, so all of these parameters, you can take it from this table. And then you plug it into here, okay? Calculate this, plug it into here, 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 and then you simply give values to omega, and then you develop something similar to this. It's not exactly the same. The two formulations provide similar results, okay? I insist, the Pearson-Moskowitz, it's nice to have it because it's with one parameter. We'll see that in the evaluation. I'll just give you the wind velocity and you have to proceed. In the other case, I have to give you two parameters. So this is a very nice graph from SNAME, DNA, Vol 3, okay? This is time, and this is the surface elevation, right? So we can see that here I have a maximum, I have another maximum, that's what we call a crest. Here, another maximum. Here is something that we mentioned. This is a maximum, but it's negative. Now, we can think that from here to here, this is a period between crests. From here to the next one, this is a period also from a crest. So we call it peak-to-peak period. From the peak to the next one, period. And if you see that it is changing, okay? Now, what we can do is we can go on, get these periods, which is changing, and then take an average. But don't worry, we're going to see that there is some formulation to approximate that. What else? Here, you see that you go from the negative to the positive. Okay? So you are crossing the zero. You come down, and here, you again zero up crossing. So you can take the value of the distance in time from here, this zero up to this one here, zero up. And this is what we can call a zero up crossing period. This is TZ. This is this one. Okay? Zero up crossing. Zero up crossing. Again, you have a zero up here. So what we have to do is take this, take that, and many others, and just make an average. Okay? And don't worry, we're going to see that there are some formulations from the spectral density, what we call a moment, the moments of the spectral density function, which allows us to calculate this, even though it is a random process. These are average values. They are not precise because we see that they are changing. It's just average. Okay, but that's very useful. Okay. Any questions about these people? No? Okay. So we have a certain record, up and down, and from there we get a register. From that register, very long, very precise, we can proceed and calculate its a spectral density. And for each one of these, we see that the waves are higher in one case than in the other case. So what we do is we classify them in C states. Okay, and of course there are several scales. Okay, so for example, in this case, this is a figure taken from the literature, and you see that this situation is what we call force 4. Every time you see the word force, that means that you're using the Beaufort scale. They call it the Beaufort, the force scale of the sea. They use the force. So that's identify the Beaufort scale. Okay? And this is the description. Small waves, there are no large waves here. Becoming larger, and fairly frequent white horses. There is a white horse here, another one here, another one here. So that's because it's very high and they tend to break a little bit. That's what they call white horses. Okay, so there are more and there are less. So let's suppose that somebody asks you, okay, let's do a calculation for Beaufort scale force 4. So what we can do is we can go, and this is what you have to find. This is Bhattacharya page 104. I'm not going to accept this from you. You have to give me something better. I'm not going to accept that you present a Bhattacharya's table. You have to find something else. I found it first, before you. Okay, people. This is the C state, okay? This is the scale, the Douglas scale. And this is the Beaufort. And you can read here, wind force. Every time you see the word force, that's usually related to the Beaufort scale. And you see that in the case of the Douglas scale, is scale 0, 1, 2, 3. And the other goes 0, 1, 2, 3, 4. So the 4 scale in the Beaufort corresponds to 2 point something in the scale of Douglas. Usually I use the 4. That's, see, the 4 here will be probably the 5 here. Right? So probably it's going to be higher than this one. Now, if you say that you want to work with scale with C state 2, and you can see that here I have the wind velocity, you have the wave height, the average, the significant, and average of the 1/10 of the highest. Remember, you have several waves. You take the highest, and from those, you take the average of those, the 1/10 of the largest. See that this is, of course, larger than this one. What else? This is the range of period where it's significant, okay? So to the left or to the right, probably the values were too small or too large. There was just too much information that they could consider reliable. Period of maximum energy, that's basically the modal frequency, modal period. And then here, we have the average period, D sub Z, okay? And other parameters that you need. So if I give you C state 3, you take these values and you proceed for the calculation. In the case of the formulations, for example, C state 3, you would take 16 knots for the Pearson-Moskowitz formulation. For the ITTC, you will require significant height, and also the period of maximum energy will be 6 seconds. Please, careful. This as units in English system of units. So these are feet. So you have to convert that to meters. Have to be very careful with that. Okay. For example, here I have, I'm going to plot for C state 4. Okay, let me go back. You see down here, this is for 16 knots. is you are in C state 3. So you got a little bit beyond that, okay, a larger value for the wind velocity, in this case, 20 knots. Transforming that into meters per second, I have here is 4.7, so here it's going to be probably 5 point something. That's 2 point something meters. Okay, and the frequency is 116. And I did this formulation, applied it to formulations. Okay, so here I have one is the ITTC, that's the brown, and the blue is the result applying the Pearson-Moscowitz formulation. And you see that they're very close, but not the same. Especially there are some arguments about that the Pearson-Moscowitz give you higher or longer waves with larger amplitudes. That's because you see that the maximum is a little bit to the left than the ITTC. Remember, when you decrease the frequency, you increase the length of the wave. With this, we can calculate the wave length, okay? For example, here, it's about, what, 0.9. Now with 0.9, we can calculate the number, wave number, and with the wave number, we could calculate the length. Okay? Questions about this process, people? Let's take a break. We are 15 minutes short of completing the class. Mr. Zamora, would you please stop the recording? So